Okie dokie. So I know today's a work day, but I did have something I wanted to talk about briefly. So I have posted the next project assignment. So this is due July 9th. That's 2 weeks from Saturday. And so what we're going to be doing is we are going to be parallelizing we're going to be writing a completely new parallel Jacobi code using MPI. Like I talked about yesterday, we're going to be doing this using domain decomposition. And let's make this bigger, shall we? Oh. Okay. I've given you in this PDF, which is now on Canvas, a basic algorithm of how your MPI program will look. Okay, you're going to start MPI, determine the number of processors and the local rank, at which point then you need to set up the Cartesian communicator. And it's using all the functions I talked about yesterday, and that's in the lecture slides. Then you need to find out what your new rank is. You need to find out what your IJ coordinates are. You need to find out who your neighbors are in all 4 directions. And then you need to determine the total size and extent of your particular subdomain. After that, you need to allocate your data arrays, your local data arrays, to the correct size. And you also need to include your ghost nodes. I talked a little bit about that, but I think I was a little confusing, so I'm going to go over that again. And then after that, you need to initialize your local data arrays, and remember to take into account the boundary conditions, because some processors will not be on the boundary. They'll be on the interior, and so they will not have any boundary conditions, whereas other people will, and so you need to account for that. At which point you're going to start your Jacobi iterations. I should say items 1 through 9 are kind of like, that's the hard part, honestly, is getting all that stuff right. After this, then you solve your local nodes, compute a local RMS value. Then you need to compute a global RMS value, and this should be done probably using an all reduce. And then, of course, if it's less than the convergence limit, you can stop. At that point, then you need to exchange your ghost nodes. So here I have a little picture. We have a blue processor and a red processor. And so the blue processor owns everything on the left. The red owns everything on the right of this dashed line. But the red nodes need to know these values on the blue nodes and vice versa. And so on blue processor, he's actually going to allocate one more row to store those values. And he's going to kind of use those as boundary conditions. And vice versa on the red, he's going to allocate one extra row to the left to store the blue node's values. And those are called ghost nodes because they don't actually get solved, but you do need that information. And so that's going to be the hard part. As far as what to turn in, I want you to do a weak scaling study. Start with n nodes equals 100, number of processors is 1. And then do the weak scaling study with 1, 4, 9, 16, and 25 processors. And if you notice, those are nice squares. So the Cartesian stuff should work just fine. However, since King's Peak nodes are only go up to 24 cores, you will need to make sure you ask for 2 nodes so that you can get that extra core that you're going to need, or multiple if you're only using the 16 core nodes. Again, as always, a report in your code. The report should include a plot of the measured speedup against Gustafson's law, estimate and report your code serial fraction. When measuring time, you want to use the MPI W time function on processor 0 to measure the time of your Jacobi iterations. I want you to compare the scalability of your MPI code to your OpenMP code, and then answer the question, what could you do to potentially improve the scalability of your MPI code? So I want you to submit a makefile with 3 targets, all which will compile your code, clean, and run. And run will run your code using 4 processors. Okay. So there is that. I'm going to send out an email on, to let everyone know that I've done this. I know I said I wasn't going to, but we'll see how this goes. So for the next couple weeks, we're going to be focusing on this. So every day is going to be a work day. And then, but I will still be posting videos. I'm going to be talking about a lot of other stuff. Let me show you what I mean. So I have posted a PDF called Programming Topics. Let's see if it loads. Alrighty, so this PDF should be fairly straightforward. I'm not going to cover all of these. We definitely don't have time to cover all of these, but it's a bunch of stuff that I think is useful to know. If there's a specific topic you'd like me to cover, please let me know. Today I'm going to talk about this section here, the coding style. So whenever you are writing code in general, I should say, first off, scientists and engineers are kind of infamous in the programming world for being horrible programmers. 1, because we've never taken a class. 2, because we don't care. We just want the stupid thing to work. But at the same time, though, if you've ever tried to use someone else's code who is an engineer, it's generally really hard to figure out. And reading someone else's code is always going to be hard because it's not yours. But a lot of times you come back to a code. 6 months later, you come back to it and you sit there and stare at it and you're like, what was I thinking? What is going on here? I have no clue what's going on. And so these coding style standards, pseudo standards that I'm going to talk about today are really important, just so even you can use your code again, or even while you're coding it, for you to understand what you're doing, and organize things in your head and on the computer. So I'm going to I'm not trying to toot my own horn here, but this is the only way I know how to do this, is to give you examples. So, all right, first off, your code is a book, all right? It's like a book, a novel, and you should be able to read it fairly straightforwardly. And we do this. One of their major tools in this case is going to be indentation and white space. All right, I get a lot of codes. I see a lot of code. Whoops, that was not what I wanted. I see a lot of code that looks like this. All right, this is not good. It's hard to read. It's hard to follow. Most of you actually indent your stuff pretty well. But it's I don't know a proper term for this, but I'm going to call it paragraphing. that makes it really hard. So if you think about your main function would be like your narrator, okay? And he says, okay, so there once was a double, and this double was sent to this function, and he came back out of that function changed. And so when you're looking at this, even this, I tend to think of this like paragraphs. So for instance, this loop body right here, this is a single paragraph. And it's surrounded by white space. It separates it from the next paragraph. And each paragraph has a purpose. So this one paragraph here, he computes the next iteration. And he also computes the RMS values. Whereas this paragraph here, he does all this stuff that he needs to do in a single region. Here's a teeny tiny paragraph that breaks out of the loop. Here we have a very clear while statement, and we have a parallel section, a parallel chapter that contains all of these other smaller paragraphs. And so if I had done this like this, maybe it's not that bad, maybe it's not that hard to read, but it's still, personally, I think, is easier to read when we can say, okay, there is a while loop. So now we're going to go in here, we've got a barrier, we've got a single region. Okay, so this is done by only one processor. Everyone sits and waits at the end here. Then everybody goes to the next paragraph, and we do the loop. And once we're out of the loop, then we have another single region. Okay? And so that's, if you can get a system down for your white space and your tabbing, your indentation, that'll make your code a million times easier to read. Naming conventions. Generally, I mean, there's no rule, hard and fast rule enforcing anything, but you can write your stuff in your names in camel case, where every word starts with a capital letter. I have that right here. Or you can do it in snake case, which you see an example here. This is from the standard library, numeric underscore limits. That's called snake case. So basically, use a naming convention and stick to it. It makes it easier to follow your code because you're not sitting there jumping back and forth. It's almost like using a consistent font style in your book. Okay. Use descriptive variable names. Now, what I mean by this is, let me open up this one. All right, no good examples in here, really. But, so I have a variable here. It's called file name in this output function here, okay? I could have called that F, and it probably would have been fairly straightforward what I was talking about. But if I'd never seen this code before, and I come across void output const string, so we have a constant string reference F. Okay, so what is F? F is probably a file name, because down here it gets used as, well, we're sending it to a file. So yeah, that would make sense. It must be a file name. Okay, so that's not that bad. T obviously is not a very good name, but now I can go and read this and say, okay, we have a function called output. It's probably outputting a file. That's what it's going to do. And we're giving it a file name, and then we're giving it an array, a two-dimensional array. We're going to call that T. And then we open the file with that particular file name, and we shove our array into there. And then we close it all off with Well, yeah, so that's what that does. Shoves the file name, or shoves T into the file. So it reads very nicely, and it's easy to understand. In this case, I don't need any comments on this because it explains itself. Okay. Obviously, I don't have comments in here at all because I was going quickly, but that's the other thing I want to talk about. Comments. If you've followed all of these rules, your code should be fairly straightforward. It shouldn't be hard to understand. The comments should be there to describe only funky things that you had to do, or maybe a hack that you had to throw in there, or describe the general overarching algorithm. I've seen people put an int n and put a comment. Number of nodes. It's not really necessary. We all kind of know what capital N means in these cases. For instance, if I was writing a function to compute density from the ideal gas law, you should put a comment above the function that says this function computes the ideal gas law using this formula, and then you write out the formula. Okay? But then after that, you don't need to, you can use your variable names could be P, R, and T, because at that point, if you don't know the ideal gas law, you can go look it up and figure that out. Okay? And in general, as your functions get smaller and smaller, your variable names should also get smaller and smaller. You should save the big, long, descriptive variable names for your general functions that kind of control everything else. And this is the other thing I want to talk about. Use functions. Don't be afraid of them. Okay, functions structure your code, they organize it, and a function should always have one purpose. It does one thing, it does it really well. And a function always makes a promise. It says, I will give you the square root of this number. And if I can't give you the square root of that number, then I will give you an error or a nan. Either way, you choose to do that. Don't be afraid of functions because they help you structure and organize your code. And my example here is, here's my main function. All right, this is where everything starts. And we start with my array. And then we do some initialization stuff. And then I say call Jacobi. And it takes the array, and it takes how many processors I want it to use. I want it to use 1. And so then I can go look up my Jacobi function, and it actually performs Jacobi. And what it returns is how long that took. Stats is a structure that I put together. It's pretty simple. It has a wall time, iterations, and time per iteration. And if I want to do it again, all I have to do is call it again, this time with 2 processors. And then I can output all of my times that I've saved up, all because I put Jacobi in a function. Most of you have not, which makes the modularity of it difficult to use. It's very hard to change it if you want. And it makes my main function look nice and clean and simple. So then talking about C++ in particular, by convention. Again, there's no hard and fast rules with this, but generally a class name starts with an uppercase letter. Functions start with a lowercase letter. If you have a constant, either a const double or a define, you declare them as all uppercase. And so that way when you're reading it, you're reading the code, you can say, oh, that's a constant. It's not going to change. However, I have seen people I haven't seen it. I've heard of people doing this, where you say define 1 as the number 1. That's kind of ridiculous. That's 2 extra keystrokes and doesn't really help the situation. And you can do that with enumerations as well. Anyway, so that's kind of the little thing I wanted to talk about. Coding style, how to make your code look nice, and keep it structured and organized so that you can understand it and someone else can understand it. And believe me, if you follow these guidelines later on in your life, I know you don't think you're going to ever have to program, but you might. And if you follow these guidelines, everyone else will thank you for it. Anyway, that's my little lecture for today. So have a good weekend. Good luck on the MPI project. I will be available by email, and we will see you later.